Okay, peeps, this is where we left off, and we talked about generating a calibration curve using Excel. And there's a calibration curve that we ended up with the last video. We deleted one point because it didn't quite fit the rest of the set. That made our R-squared value better, which is what we use to figure out how straight of a line is it. And we ended up with a 3-9er, 0.999. And then we had this equation up on top that says 0.0575x minus 0.1239. We've not really talked about what to do with that yet. And we've not really talked about what to do with our samples yet. We just talked about how to make the graph. That's how we make it. Alright, so what I've done is that on my notepad, I have basically written this equation and this R-squared value down so we can do some stuff with it. And here it is. Same data that we generated with the graph. Remember, we ran a sample. That sample was 0.713. And then here is my y equation and my r-squared. So now it's my job to treat my samples and to figure out what the concentration actually is, right? What is the actual number for the concentration of the sample? I got to know how to do it. Well, all of the work's basically been done for us already. I just need to be able to use a little bit of algebra in order to solve for this. Okay, so the r-squared value, that r-squared value I don't do anything with anymore. The only purpose of the r-squared value is to figure out, is it linear? Do I have a line, yes or no? Once I do that, I do nothing else with that number. Forget about it. It's the only purpose in it. Now I need to focus on this equation that came from the regression line. This equation represents the line that was drawn on the graph. So the rules of algebra state that if I go to this graph and I try to find any type of absorbance, absorbance was on the y-axis, right? If I have an absorbance of 6, right there it is, I can go over until it meets the line and then come down to figure out where on earth I would be at as far as the concentration. Right? There, on over to the line, I'll be able to get the concentration that's present. Well, that's estimation. We're better than that. We don't have to estimate things. I mean, that's the purpose of this equation right here. Right? So I'm going to minimize this screen down. And I've got this equation. And remember, we ran a sample and we got an absorbance. All right, well, this is an absorbance. And absorbance, look, went in for the y-axis. So that means in this equation, the absorbance is represented by the y variable. Hopefully that makes sense. X is concentration, therefore X in this equation is concentration. Y was plotted on for the absorbance, so in this equation, Y represents the absorbance. So 0.713 goes in for Y equals 0.0575x minus 0.1239. Well, I need to solve for X. X is my concentration, and that's what I'm trying to find for my sample, right? I'm trying to find X, the concentration. That was on the X-axis. So to get X by itself, we're first going to have to get rid of everything else around it. So I'm going to add 0.1239 to each side of the equation. So I'll bring my calculator up. 0.713 plus 0.1239, and I hit enter, and I get 8369. So 8369 equals 0.0575x. Well, that's 0.0575 times x. So to get x by itself, I do the opposite of. So I divide by 0.0575. So x is equal to 0.8369 divided by 0.0575. Hit enter, and I get 14.55. I'm going to round it off. 14.55. Okay, well, what does that number mean? Well, if I go back up here, x represents concentration. That's what was on the x-axis. The concentration unit was part per million. So that means that my sample is a 14.55 part per million concentration. We kind of already estimated that in a way, right? 0.713 we said would fall right in here between 0.5 to 1.5, in between 10 to 30, and it just so happens that 14 is in between 10 and 30. So we kind of estimated where it would be. We didn't know really what the exact number or concentration would come out to be, but by plugging it into that equation, we are able to solve for those sample concentrations. And that's how we treat all of our samples. So if I had maybe 5 samples that I ran on the instrument, I would take each one of the absorbances for each one, 1 through 5, and I would plug them into here individually, just like I did here with the first one. Go to the second sample, get your second absorbance, plug it in for Y, solve for X all over again. Go to your next one, plug it in for Y, solve for your absorbance all over again. You can do that by hand, write them all down, put them on a data sheet, turn it in. Or Excel will do it for you as well. So let me show you how to do Excel version of a calibration curve. It will clear up a little bit of work for you, is what it will do. All right, so here on this screen, I'm going to come down here to the very bottom, and I'm going to do Y equals, and I'm going to put all my numbers in a separate cell. I'm not going to put anything else with them, just the number. So 0.0575, that's my number, that's it, that's all that goes there. In this one, I'm going to put X minus, and then in this one is just going to be a number, 0.1239. So I'm going to get Excel to do the work for me. So I'm going to scroll down, and we said that our sample number 1, I'm going to put S1 for sample 1, was 0.713. And that's where I'm going to put it here for Y. Y equals right below that, right? So I want to know what is my concentration after I solve for that. Well, over here to the side, I'm going to put bracket X part per million. And this is where I want my answer to go, right underneath that column. That way, sample 1 is associated with the absorbance. And then in this cell, that's going to be the concentration of the sample. To do that, Excel needs to understand that you want to do a calculation. So you're going to start off with the equal sign, right? That is the trigger. Oh, they want me to do a calc? Okay, I'm ready. Give me the numbers. Well, what happened here is that we took our absorbance, the Y, and we added the 0.1239, right? That's minus 0.1239, so we did the opposite of. We added 0.1239. I'm just going to click that number. That automatically relates to Excel that that's the number I need to use, and that saves me from writing it again, right? Well, we need that to be done first. So up here in this formula line, I can click this and modify it at any point in time. So I'm going to put a parentheses around that. That way Excel understands, oh, they want me to add that number first. Now what do they want me to do? Well, up here in that formula line, I can continue on with it. No big deal. After that, we said 0.0575 times X. Well, the opposite of multiplication is division. So I'm going to divide. That's the purpose of the bar. And I'm going to divide by 0.0575. So I'll just click that number. Again, if there's anything else in there besides the number, Excel doesn't know what to do. That's why I only put the number in the cell, and that's it. All of the variables, everything else, don't put them in there. Excel won't know how to handle it. Then I'm going to hit enter, and I get 14.55 as an answer. So let's say that I have ran 5 more samples. S2, S3, S4, S5, and S6. And each one of these has their own absorbance value. So let's say the second sample ran at a 1.45. This one was a 0.114 or 112. This one was a 15.4. This one was 8.44. This one 3.46. Do I got to do it every time? The answer is you can, but no one wants to take the time to do all of that, right? So here's the shortcut. If I click this cell that I did this calculation in right there, these numbers are going to highlight again. Something's not going to change here. If I wanted to solve for the 1.45, I would do the same process, right? I would put 1.45 in for y. I would add this number, divide by that number. The 0.112 is the same way. I would plug in 0.112 for y, add that number, divide by that number. I do that all the way down. Notice that these two numbers are not changing. All right, well, if I wanted Excel to do that repeated calculation, the only thing I have to do is go up here to the top. This 0.1239 is showing up red, so that F21 is also red. Look, here's the F column. Scroll down, there's row 21. That's what that's referencing to. So if I put a dollar bill, dollar bill, y'all, in front of F and in front of 21, that it does what we call anchor. It doesn't change that position. It's always going to reference that 0.1239 every single time. And then I always want to reference this 0.0575. We're using that in every single calculation, right? So I'm going to put a dollar bill in front of the D, and I'm going to put a dollar bill in front of the 21. I've now anchored those two. And then I hit enter. Notice my 14.45 didn't change. But now what can happen is that I can click this cell, that little box into the right-hand corner. I can click that box and then hold down your left mouse and drag it down. And it will highlight all the boxes and then let loose of it. And it does all the calculations automatically. There you go. That saved you a lot of math. It saved you a lot of work, and Excel did it all. If you go down through here and click on a box and just go up and click in the formula sheet at the top, it's going to show you what it did. It used 1.45, 0.1239, and 0.0575. The same thing for this one, right? It used 0.112, 1239, 0575. So it did the calculation like you did the calculation the very first time. It just repeated it. That's all that it did. All right, so now I'm going to do something a little bit different, and I'm going to show you why the anchors are important. So here I'm going to type in the equation again just to review it. So I'm going to hit equal. I'm going to open the parentheses up, and I'm going to say take this, and then we're going to subtract, or sorry, we're going to add this number to it, close it up, and then we're going to divide by 0.0575, hit enter. Let's say that I didn't do an anchor. I forgot to do it in my step. And I've got all of these samples that's listed over here to the left. And I'm going to say, hey, I'm going to do the same calculation. So I'm going to click the 14.55, click the box, drag it down. There we go. Well, why is it doing that? It says cannot divide by 0. Well, it worked for this one. Why didn't it work for those others? Well, click in the cell. I'm going to click in this divide by 0. And up here at the very top, I'm going to click the formula. And look at what it did. Because you drug it down, and because you didn't anchor the number, it's going to think that because you went down one space, it wants you to do the calculation down one space from that one and one space from that one, which was the originals. That's why it says cannot divide by 0. There's nothing there. Now, what if there were numbers there? You would have never picked that up. It would have gave you maybe an answer, and you would have assumed that that answer was correct. This is why it's very important to anchor the numbers if you're going to do a repeat calculation. Right, so if I come down here, the same thing's going to happen. I go up here to the formula sheet and look at what it did. It took that 8.44, which is what it should have done, but because I moved down 1, 2, 3, 4 spaces from the original calculation, it thinks that I want to move down 1, 2, 3, 4 spaces from that number and 4 spaces from that number. That's not what I want. I want those numbers to be used over and over. And that is why we always have to put in the dollar bills or the anchors to those numbers. I don't want it to change. And that's the purpose of the dollar bills. All right? So don't let that catch you for a loop. Don't let that throw you off and cost you tons of points because you weren't clever enough to go in and anchor those numbers. Now, you can manually put them in. You can go down through here and manually type in that calculation every single time. Take this number, add this number, divide it by that one, hit enter. In the next one, you do the same thing. 3.46, click that number, divide by that number, hit enter. And that will give you the right answers. But it just takes a lot of time. And when we've got a lot of things to do in a lab, we don't want to waste our time on these calculations that are showing up in these spreadsheets. So if I can quickly just anchor those values that I don't want changed, that I'm going to be using over and over and over, if I can anchor those and then just click and drag, you saw it took a couple of seconds to do 6 samples that were analyzed in a lab. Now imagine if you had 200 samples in a lab. 500 samples in the lab. You're not going to want to do that by hand with every single one of them. You're going to click and drag. You're going to automatically let it populate, and that's what it does. All right? Okay, so that's a little bit more about Excel and about a calibration curve and how to take sample data that I would get from the machine and correlate that to the standards that have been ran using the instrument. Okay? So what you're going to find out in these assignments, especially in the very first assignment with calibration curves, is it's going to want you to make a calibration curve. So it just wants you to plot the X and plot the Y and give me a graph. That's all that it's after. A little bit later on, you'll start plugging numbers in to the equations, but we just want you to feel comfortable about plotting cal curves first. And that's what a lot of the first assignment is going to be.